magic classification theorem that I can manage to put into my time. So that will be somewhere in the middle. I will start talking about Ratner's magic classification. But some of the special cases so some of the special cases have been known before, and they are easier to prove, and theorems of Fürstenberg and Dani, so I will talk about those. And they really use a completely different argument, which relies on knowing what's going on when you use the dynamical system that is the geodesic flow. So I will have to talk about the geodesic flow, and this means I have to tell you about H and SO2R and measures on these, etc., etc. This is where we start. Good. So what's the hyperbolic plane? What is H? H is, as a set, it's defined as all complex numbers which have positive imaginary part. So that's the upper half space model of the hyperbolic plane, not including the boundary. You can also define some nice meromorphic, some nice rational function which maps the upper half plane into the disk. So you could also define it H as the open disk. And some of the pictures you see in hyperbolic geometry, or visualizing somehow what's going on in hyperbolic geometry, are much nicer when you view them in the disk model. So you can produce nice, beautiful pictures this way, but let's talk about the mathematics instead. Right, I need to make H into something else than just a subset of the complex plane. I need to define a distance notion so that I have something hyperbolic going on. And the way to do this is to define a Riemannian metric. Let me write down the formula and then explain what this formula does to you.
Can you use a pen? Can you use another pen?
Yes. And the pen says I can leave it open for 48 hours without letting it dry out, but maybe that time has passed. Is there a trash bin somewhere? There's one. Right, what do I do with this formula? If I take 2 points, this point here and that point here, and I want to know the distance, I first look at paths that go from here to there and are piecewise smooth and so on. So I take some curve going from here to there that is piecewise smooth, and then use this formula to tell me the length of the derivative, the speed at that time, right? So I look at every point at gamma of t, I look at the derivative, gamma prime of t, points some direction. I use this formula to calculate what the length of gamma prime of t is. And then distance traveled is the integral of the speed at time. So I look at this formula, and that's the length of the curve. And then I look at all possible curves going from here to there and try to find the shortest. If there's a shortest, I would call it the geodesic, and then calculate the distance of these 2 points by calculating the length of the geodesic going from here to there. And that actually works out, and you get a geodesic that looks like this. Something like this. The point is it should be a half circle touching the boundary in a normal angle. Yeah, hitting the boundary at a normal angle. Let me specialize the 2 points a bit. And then it's completely clear why this should be the answer. If the 2 points are on the y-axis, this is my point x1, or let me call it z1 because it has an x-coordinate and a y-coordinate. This is the point z2, and I choose them on the y-coordinate, y-axis, so that the y-coordinate is 0, x-coordinate is 0, and then it would be completely stupid if this is my formula for the length of a tangent vector. It would be completely stupid to walk sideways, right? The best thing is to walk straight up. And that would be the geodesic. Okay. In a little while we will see why this is the correct picture for 2 other points. Okay? To see why this is the correct picture for 2 other points, I need to tell you why this metric is really special. And this Riemann metric is really special because it has a huge group of isometries. I mean, if you can cook up other definitions of Riemann metrics, and then you wouldn't have maybe any isometries, and then I wouldn't be able to tell you anything about the associated geodesic form. But this particular formula has a huge group of isometries. So is a transitive group of isometries on H. So I can map any point to any other point by an isometry. It's transitive. That's huge, right? Now, why is that? Well, I can give you a formula. Let gamma be A, B, C, D, P in SL2R. So I take a determinant 1 matrix with real entries. Then I define gamma of Z. I write it as a dot because I want to emphasize that it's an action. Gamma of Z I define as AZ plus B, CZ plus D. Let me tell you briefly why it's an action. What do I mean by it's an action? That's the first question. If I have 2 matrices, eta and gamma in SL2R, then I could look at eta applied to gamma applied to Z. Or I could look at eta multiplied by gamma and then applied to Z. And they're the same. That's what I mean by I have an action. And let me tell you briefly why this is the same. I could identify Z with Z1, with the vector Z1. And if I identify Z with Z1, then I can apply gamma to the vector. That's very easy because gamma is a matrix. It acts naturally on vectors, right? So I get A Z plus B, C Z plus D. But what do I identify this with? Well, I should identify it with the number that I've written here. What's the identification or what's the equivalence relation? The equivalence relation is just homophatic. So I think of it projectively. So this point is equivalent to AZ plus B divided by CZ plus D, 1, and hence, secretly, this action, which is called Mobius transformation, is just applying a matrix to a vector. And hence it's an action because we already calculated in linear algebra that this law is correct. Multiplication of matrices really corresponds to composing linear maps. Right. Now there are some things to calculate, which I will not calculate because they're really calculations. So the first thing to calculate is that this image here, this gamma of Z, is really in H. Nobody stopped me when I said I want to wrote down this formula, but this is my space and I want to give you a group of isometries, then this is better true, and it is true. But it's just a calculation. Maybe you could cheat and say it must be clear, right? It's completely obvious. Why is it completely obvious? Because SL2I is connected, and the outcome is never real. So if you start at the identity, gamma equal to the identity, then the Z, which is in the upper half plane, is mapped to Z. And if you now walk in the group to gamma, you never get a real number along the way, so you probably stay up there, right? You could also do the calculation. The second fact that is crucial is that it really gives you isometries. And for this, you need to work, of course, with our definition, with our Riemannian metric. So you really have to look at this formula and then take the derivative of that transformation. Because that derivative tells you by the chain rule how it's going to affect tangent vectors. So you you take your gamma, damn it, nobody stopped me, someone should have stopped me. Gamma is of course not a gamma because gamma is a gamma over there, right? So let's change some of the gammas at least to g's so that the following formula makes sense. Right. What you need to calculate is the following. You want to calculate the length of G composed with gamma. Previously it would have been like that. And G is the supposed isometry, and gamma is the path linking 2 points. And you just plug this into this definition. Then you need to calculate the derivative. You need to work with the notion of lengths at gamma of t and G of gamma of t. And you will see that it all works beautifully out, and you get that the length of curves is not changed. After you've done this, you think back what our definition of the distance function really was. We took an infimum over all possible curves. Well, obviously now, because the length of curves is not changing, the distance is not changing along the action of any G in SL2R. Now that you know that, you can answer, okay, why is it transitive? Right? Transitive. What does transitive mean? Transitive means that any point I can map to any other point. Let me tell you why I can map I to any other point. And if I can go anywhere, then any other point can go to any other point because a group is acting. By the way, you're allowed to interrupt me at any time, and please do so when I make mistakes or when there is a confusing point. Otherwise, I'm just assuming that it's too easy and I will have to go fast. transitive. It's very easy. I just define a particular point G where maybe I want to I write it as a product of two matrices and I apply them separately, one after the other, already knowing this law here. Right? So now I apply G to I. And I get 1x1. Apply to, now I need to apply this point to I. I plug it into my formula. I get a quotient, square root of y, I, plus 0, 0, plus 1 over square root of y. Well, I chose it precisely such a way so that this becomes yi. And now I apply 1x1 to yi. Again, I have to put it in the correct formula. I get yi multiplied by this 1 here, plus x divided by the 1 here. Matrix entries that I don't write as zeros, in case you were wondering. This is x plus iy. The only restriction on the y that I have used along the way is that y is positive. So this is an arbitrary point of h, and I'm transitive. It's actually more than transitive in some sense, because I didn't have to use somehow all of SL2R. When I take the product of this matrix and that matrix, I get a matrix of that form. A triangular matrix. So there's another group that is important in the discussion and that I didn't use. And it's a big subgroup of SL2R, and that's SO2. Sometimes this triangular group is called D for Borel subgroup, or maybe it's called T for triangular, but T maybe is less good for other reasons. Yeah, while I'm at it, maybe I give you a few more abbreviations. A stands for the diagonal subgroup. But let me say that I want positive entries. And N stands for this group here. These are all groups that will feature a lot in the discussions. And then there's K, which is SO2, which is the orthogonal group into the matrix. And that's isomorphic to the circuit group or to the torus. Right. Now, how does this act, this K? Say on I. Somehow we will start using I as our reference point. I mean, it's a plane, right? And we have one point. At least once you know that there's a transitive action, any 2 points look alike, right? Because you have a transitive action of isometry, so it really is a plane where each point is equivalent up to an isometry to any other point. So we just take one reference point, which we choose our origin, and I is this chosen origin. How does K act on the origin? Well, it's simple. Short calculation tells you K completely doesn't do anything to I. Let's do the cosine phi I minus sine phi I divided by no I, yes, thank you. Someone is watching me, that's good. Sine phi I plus cosine phi, and then you play with the sines and you get that it's I. Yeah. Now, let's put a set back in where the I used to be. And let's take the derivative. Right. Sooner or later we will have to talk about tangent vectors. Why? Because I want to define the geodesic flow. If I give you a point in the plane, what does the geodesic flow do to it? Well, it's a stupid question, right? Because if you have a point and nothing else, you don't know which direction to go. So, to have a geodesic flow, you need to have a point and a direction. Then you can start walking in this direction. So, we will not have a nice action on H. Well, we have one. That's our SL2I action. But somehow this will not be our geodesic flow. That's a group of isometries. It doesn't have anything to do with the geodesic flow. So we need to talk about tangent vectors. And we already know that our SL2I action preserves the lengths of tangent vectors. So at some point we will start talking about unit tangent vectors, meaning tangent vectors that have length 1 at the current point that you're attached them to. So the plane, the picture is not just that, it's somehow all the points there with all the possible directions in all possible points. So that will be our space on which we want to do stuff. And this we will define as T1H. And when you go close to the boundary, then the Y is very large, and that means that you have to draw your vectors a bit smaller. And if you're very high up, and you want to draw the vectors of length 1, then you will draw them much bigger. That's somehow the hyperbolic metric that dictates how the picture should look like. Okay, so, and we already have an action on T1H, because SL2R acts on H by this formula. But this formula is very easy, and very concrete, and differentiable. So I can calculate the derivative, and then I know how the SL2R acts on tangent vectors and unit tangent vectors. Okay. Let me finish that story here. What's the derivative? It happens, it then turns out to be just that. Even for ABCD, even if you take this derivative, you just get 1 over c z plus d squared. That's your derivative. Which of course you should think. So here you have z, and you have a tangent vector, right? And then you have g times z, and at g times z, you need to know the z goes to g times z, and the vector v goes then to gz derivative at z, which is just a complex number multiplied by v. And that will be some other vector of some other length in some other direction. A Euclidean of some other length, but hyperbolically of the same length. And the factor you need to multiply with on the level of the tangent vector is this factor here. And if z is equal to I, then because the base point is not changing, so the difference between hyperbolic length and Euclidean length is not changing, then luckily what you get here is a complex number of absolute value 1. So it really matches with what I said earlier, that the derivative action on tangent vectors doesn't change the length of the tangent vectors. If you take into account the possible change of base points. Here the base point is not changing, and we just multiply it by a value, number of absolute value 1. Okay. If you haven't seen this before, then it's a bit something to swallow. I do. But I have to set the ground somehow, and I try to do it relatively quick because I want to reach other topics. So, are there any questions to these rushed topics? So let me summarize quickly while you think about the possible question. What did I say? I told you that there is a nice object, namely the hyperbolic plane, with a nice definition and a nice definition of a length of derivatives. Using this, you can define the distance of points, and just ad hoc, you can define this action on the hyperbolic plane. And then check by the calculation that I didn't do, that it doesn't change the length of curves, the length of tangent vectors, if you apply the derivative action on the tangent vector level. So you get an action of SL2R on the unit tangent bundle. Somewhere I had a unit tangent bundle. Now we have SL2R acting on it. And the action is transitive, which is great, but not simply transitive, meaning, for instance, I has a huge stabilizer. And actually, you can use the same calculation sort of backwards and realize that the stabilizer is precisely SO2. Okay. Are there any questions to these concepts? Good. Or not so, depending on how you feel, which I can't tell unless you ask questions. Okay, now it's not simply transitive. What does simply transitive mean? It means that there's a unique group element that maps point Z1 to point Z2. That's not true because of this huge stabilizer of I. But you can ask, is the derived action of SL2R on T1H simply transitive? Which, of course, again brings us back into this question here. Namely, we saw that this is the action on the tangent vectors if your base point is I of the SO2, right? So we ask whether this here is equal to 1, or when this is equal to 1. Well, since there's a square here, this is equal to 1 if the input is equal to plus or minus 1. Which tells us that the stabilizer of II, so this is in Z, and this is in the unit tangent bundle at I of the hyperbolic plane. What's the stabilizer of II inside SL2R? Well, to stabilize II, you need to stabilize the base point, which means you need to be in K. And to stabilize the direction, you need to know that this here is equal to 1. And this here is equal to 1 if the, without the square expression, is equal to plus or minus 1, which tells us that the stabilizer of II is plus minus the identity. So it's again not simply transitive. No. But it's really not very far off now, right? It's just 2 points of the group that act trivial instead of 1. And luckily, minus the identity doesn't just fix this point, it actually fixes every point. Minus the identity is -1, -1. When this acts on Z, it becomes minus Z plus 0, 0 minus Z, minus 1. That's called Z. So minus the identity fixes every point on the hyperbolic plane and every tangent vector, because when the action is the trivial action, then the derivative action is also the trivial derivative action. So that means also, because plus minus 1 is a normal subgroup, I can just take the quotient of SL to R by plus minus 1, and now I can identify my hyperbolic plane with a group. The unit tangent bundle of the hyperbolic plane with a group. It's called projective special linear group, and it's just defined by SL to R, mod the normal subgroup plus minus that. Normal central subgroup plus minus that. Okay. Are there any questions to this? Let me now tell you why the geodesics really look like this. Those are the geodesics. One geodesic we already know, namely this one. This is a geodesic. Whenever we have a vertical line, we calculated, we convinced ourselves by not calculating it that these are geodesics. And the correct parametrization of this geodesic, let's say this is I, then the correct parametrization of it should be either the t times I, comma, either the t times I. And this should have been I. I take the vector pointing north at I, that's my reference tangent vector. And that point I identify with the identity. You could have chosen any point. But if you make a different choice, all my abbreviations go down the window because they rely on making this particular choice. And if you choose a different reference vector at a different reference point, you're just conjugating the groups that I defined by some matrix. It doesn't matter, this is the simpler choice. So, by calculating the length along such a path, you realize that this is the time one parametrization, or the unit speed parametrization of this geodesic. Either the TI, either the TI. That's the unit speed parametrization of the geodesic going through the y-axis. What happens when you map, when you apply an isometry to this geodesic? You get another geodesic. And the Mobius transformations AZ plus B, CZ plus D are holomorphic, and they're really, they're much easier than that. They're just linear divided by linear, and these have the special property that they map lines to lines or circles, and circles to lines or circles. And they preserve angles, right? So if we, and they map the real axis to the real axis, because if you plug in here real number and here real number, then you have a real expression because everything else is real. So the boundary goes to the boundary, and the angles are preserved. So the other circle has to also hit the boundary in a 90 degrees angle. So, and because this group is so big, you really can map any such half circle to a vertical line, to the y-axis if you want. And because of that, the geodesics really are described by these pictures. Okay? And the geodesic flow is the following. What does the geodesic flow do? The geometric description is take set I, draw the unique geodesic through Z in direction ZB, sorry, arbitrary direction, in direction B, and follow it for time t. So it's a flow. It's a one parameter group that acts. It's really continuous time. In the morning we defined a dynamical system as a map, a discrete map with discrete time, not discrete space, but we had a compact topological space, and we had one map that we can think of as how the system behaves one time unit later. Here we have continuous time, but other than that, it fits really nicely into the morning session also. So we have continuous time, and then we have our unit tangent bundle, point and vector, and we map time, point and vector to point and vector along the geodesic t seconds later. We could cook up some notation for that new point, new vector. We will have a formula, don't worry, but from this description it's not yet so clear what the formula really would be. It's not really the Mobius transformation. Some sense it's something else.
But since you have given us already one example,
yes,
you are trying
right. Once you know how it works on one example, you can use the transitive action to know how it works on all examples. So that's why I wrote down the parametrization of one example. However, what I want to do is I want to phrase this example not on T1H, which is annoying in some sense. I want to phrase it in terms of PSL2R. So I want to understand what, for the reference vector, this definition means in the language of PSL2R. II goes to e to the t I, e to the t I. II corresponds to, under the isomorphism to I, to the identity, because that's my reference point. What does e to the ti, e to the ti correspond to under the isomorphism to PSL2R? So I need to find a matrix so that when I apply the matrix to II, I get precisely this. And this is the correct expression. If you take e to the t over 2, e to the minus t over 2 and apply it to II, you get e to the t, e to the ti, e to the ti. So for the reference vector, the geodesic flow corresponds to multiplication with the diagonal matrix. For the reference vector, it doesn't make sense to specify whether it's the left multiplication or the right multiplication, right? Because I'm multiplying the identity. There's no difference between left and right. But this correspondence here uses a particular, it makes a difference between what left multiplication and what right multiplication is. So maybe another way to ask is, when I apply a Mobius transformation on T1H, what does it correspond to on PSL2R? Well, we had the composition law, and the composition law just tells you that the Mobius transformation here corresponds to left multiplication on PSL2R. So if I now apply a Mobius transformation to this picture here, so now I'm moving to the general vector. I apply some G, then I get G II goes to G e to the Ti e to the Ti, and in the other picture it corresponds to G goes to G e to the T over 2 e to the minus T over 2. So if I now ignore everything, if I take everything here and just ignore it, then this is your definition of the geodesic flow. The geodesic flow is right multiplication by the diagonal matrix, where to match the correct speed, we need to take the diagonal matrix with e to the t over 2, e to the minus t over 2. If you forget the over 2, then you're speeding up the geodesic flow by times 2. Who cares? Okay, so we have a dynamical system, right? We have a space and a continuous time evolution of the system. And it just means you take the vector and you follow the direction it points to. You could set everything up in terms of Riemannian metric and differential equations and so on, and you get down to the same picture. Any questions? So, okay. Is this a very interesting dynamical system? Not yet. Why not? Because we are having a plane, take a point and a vector and it just go in this direction, right? But on the plane, if we do this on the plane, we just walk off, never ever come back, we never ever see anything interesting. But in the morning talks, we didn't talk about rotations on R2 or rotations on R, right? Translational R, that would have been the corresponding thing. Translating on R, we didn't do that. We factored R by the integers and then looked at an irrational translation. So we looked at the compact space. Here we have we are very far from compact and everything walks off to infinity and it's completely useless. So we need to somehow fold up our space to make it smaller so that we have some interesting dynamical system. How do we do that for getting the torus? We got the torus out of taking the real line and then factoring the real line by some isometry. The isometry was just translation by 1. And then we got the smaller space, namely the torus. So I want to find, possibly, at discrete subgroups of the group of isometries that I can use to fold up my space into something smaller. Right. So suddenly we can talk about gamma also. This will be the role of gamma. This was G. So in some sense you can you can say that this introduction that I'm giving you is an introduction to G mod gamma, right? And G we already saw, and now we need to see gamma. To fold up the space. The most important, nicest and everything example is, let's take gamma equals to SL2Z. And then, and define M equals H modulo SL2Z. So that's just the group of, the set of orbits, right? It's the gamma orbits of point Z in the hyperbolic. But of course that's the abstract definition. Maybe it's not so nice to think of it in this way, because then every point is sort of this cloud of points that's annoying. So instead of that, I want to convince you that there is a much nicer, easy picture that tells you perfectly well what this quotation mark manifold looks like. And for this, we need a fundamental domain. So a fundamental domain is a set such that each gamma orbit intersects the set precisely once. So it's a subset of H that selects from every orbit one representative. And then I can identify the surface with that set. Of course, possibly I would destroy some structures like Riemannian metric and so on if I do that, but it gives me a picture, and then I may have to talk about gluing rules. Right? For the torus, for the one-dimensional torus, that set would usually have been chosen a half-open interval 0, 1. But I would also remember in the background that 1 used to be equal to 0. 1 is now outside my fundamental set, but the topology is affected by 1 is actually equal to 0. The same thing I want to do here. Maybe ignoring the boundaries altogether and letting you worry about them if you want to. Okay. I draw the fundamental domain. A fundamental domain. I shouldn't say the. A fundamental domain. The usual one is given by, and that's a picture one sees a lot in number theory books, or at least should. I draw free geodesics, right? We talked about that those are free geodesics. And then I look at the triangle that is enclosed. That's the fundamental domain. Let me call it F. I'm claiming that this F is a fundamental domain for this quotient. Let me point out what the gluing rules are, and then we prove the actual statement. So the gluing rules the map 1101 is just a map z goes to z plus 1, shifts on the real axis by 1, it identifies this line with that line, so it glues that side of the triangle to that side of the triangle. So there's one side left to glue. Well, since there's only one side left to glue, it has to be glued to itself. So I have to find a map that maps one half of that line to the other half of that line. So somehow the middle point has to be fixed. So somehow it should be an element of SO2 and integer simultaneously. There aren't many choices. And that would be the right one. And this identifies this side with that side. So these two I gets fixed because it's an SO2 matrix, and one gets identified to the other. It's a map Z goes to -1 over Z, and it's basically inversion on the circle, except that inversion on the circle would be anti-holomorphic, so it's not really inversion of the circle. But other than that, it's almost the same. So actually, it's inversion on the circle and some conjugation along the y-axis. So this point goes to that point, which makes sense because I'm claiming that this line gets mapped to that line. So it's, if you glue that to that, you get a tube, which is half open at some side. And then this tube gets glued to itself. So geometrically, it looks like you have this tube, and then you have two weird points. This point and that point, which is this point and that point. So I and the third root of unity, they are slightly weird, because you can calculate the angle around them, and the angle around them is not 360, but as you see here, only 180 at that point, and 120 at that point. 60 plus 60. So it's not really a manifold, it's not really a smooth surface, but it's very close to it. It's called an orbifold. Fine. Right. I'm claiming that any other point whatsoever, z equal x plus iy, can be mapped by some gamma. Gamma, now in capital gamma, an element of SO2 z, can be mapped by some gamma into the fundamental domain. Usually you find this done really as a procedure somehow. In the books you prove it like this. You first try to maximize the y-coordinate along the orbit. And then you do various things and you prove that the y-coordinate is actually bigger than some parameter. It's definitely not too small after you have maximized it along the path. And by doing a bit more and then shifting left and right, you end up in the fundamental domain. That's the usual proof. The calculation is a bit messy. You really have to write down the formula and see what it means, and then you find an integer. Let me suggest a slightly different approach. But maybe before I do that, I should tell you that there is there is a map that sends this point to itself, is integer, and rotates around this by 120 degrees. Gamma special exists. I don't know it in my head. Someone can calculate it and point it out, and I'm happy to write it down, but it's not really relevant. Let's just believe that such a thing exists. And then it's actually obvious why this F is a fundamental domain. Proof that another set O will be equal to gamma F. So I take all the possible elements gamma Z for gamma in SL2 Z. I said before gamma is SL2 Z for now. And Z in F. I take all these possible points that I get from SL2 Z and my fundamental domain that I want to prove is a fundamental domain. So it contains F. It contains the tile right to it. Right? It contains also this guy and that guy. Who cares? It contains also the guy left to it. So it also contains this and to the left of it. It contains this here because my -1/z transformed this guy to that guy. So that makes it at 120 degrees around this point. And then I use this gamma special and rotate it 3 times, and I get actually a neighborhood of that point also. So by using this special one and these two, and the special one I can write as a certain small product of these two, I see that F, I don't care whether F was defined as an open set, partially, whatever, but yeah, I really want it to be a fundamental domain. So maybe make a choice. The left boundary belongs to F, the right boundary does not, let's say. F is contained in the interior of the set O. Well, a very suggestive notation, right? This interior is actually O. Why? Well, because if you already know that F is an interior, then every point Z is an interior, but gamma is an action. Right? So every point gamma Z is an interior, but the whole set is made out of gamma Z, so the set is open. Right? Anyone objects? Now I'm telling you O is also closed. Why is it closed? Well, let's check that later, but why does it finish the proof? Well, if it's open and closed in a connected space, then it has to be nothing or everything, but we know it's something, so it's everything. And that means that F is a fundamental domain. Why is it closed? Suppose Zn converges to some set. And Zn, or let's say suppose gamma n Zn converges to Z. Gamma n from S to Z and Zn from the fundamental domain. Then there exists some n with distance of gamma n Zn to Z is less than 1 over 10. Whatever. Oh, 10 is good. Which also means that the distance of Zn to gamma n inverse Z is less than 1 over 10. But Zn I know is a point in my fundamental domain by choice. So Zn is somewhere, let me draw it. Zn is somewhere, maybe it's here, I don't know. Zn or Zn. Maybe higher up is more frightening. So let me make the high up choice. Then this other point, gamma n inverse z, is a distance 1 over 10 from Zn. Well, if it's distance 1 over 10, then we should think it's like this, but it may not be. It might be something like this. The 1 over 10 wall might look like this. However, it doesn't stretch far down. It doesn't do that, because the distance of a point high up to the distance of a point far down is big. That you can calculate. But far up, you may have the freedom of travel a lot in the x-coordinate. So the balls open up somehow. The 1 over 10th balls, if you go high up, may open up more and more and more. That's okay. But they only open up horizontally, right? So this other point z is somewhere here. But if the z is here, then I just shift it horizontal. No, that's not Zn, it's gamma n inverse Zn.
It's inside.
Inside the ball.
Z. Inside the ball, thank you. But then I shift horizontally and move it into the fundamental domain, which means my limit has a representative within the fundamental domain. Done. Yeah, we'll finish in a minute or so. So the dynamics on this surface is now much more interesting. And let me just convince you what you have to think of when you want to now do the geodesic flow on the surface. So the surface looks like, I drew it before, it has one point at infinity, and that point at infinity, or the neighborhood of it, is called cusp. And then it has these two special points, but never mind. And other than that, it's like a sphere. It's a sphere minus a point, and with 2 points being weird. So sometimes it's called free-punctured sphere, because these 2 points are also weird, and 3 odd points in total. 1 missing and 2 odd. That makes 3 odd points. So if you have a point here and a vector, then you can just follow that point in the vector. And if you point into the cusp, then it will just go into the cusp for some time, and then come out again, most likely. Unless you really shoot into the cusp. You can also do that. If you point straight into the cusp on the nose, then you just walk out and never come back. And here it looks like something imprecise, but you can make everything here precise using that picture. If you draw it in the fundamental domain and you point north, then you stay in the fundamental domain and walk out. That's a geodesic orbit. Or you point almost straight into the cusp. Then you will walk high, you will walk out and out and out, and along the way you may have to shift many times by this 1101 map to stay in the fundamental domain. That corresponds to this winding here. And at some point this geodesic, because it's a circle, comes back again. So somewhere high up you turn around and then wind backwards to come back again. And there are nice things to be said about this geodesic flow.
But you have also some mixed scenario. Then you wind for a moment and then you will go to the cusp.
Yes, if you come back, so that's a nice question, nice comment. If you have some orbit like this, you walk out, you shift, then you start walking back, you shift still. At some point you hit the lower boundary here. When you hit the lower boundary, you have to apply the other isometry, the -1 over Z1. And at some point this alpha got replaced by alpha minus n, because you have shifted many times. And then you do -1 over Z, so you replace this alpha minus n, which is the forward endpoint, by 1 over alpha minus n. Has someone seen such a procedure before? Well, hopefully many of you have seen this procedure before. If you forget the minus and call this n the fractional part of alpha, which it almost is, then it's the Gauss map. So somehow the geodesic flow and the Gauss map, the geodesic flow on the modular surface, which is precisely this quotient that we're talking about, and the Gauss map, they are very much related.
Yeah, you can relate it to the continued fraction expansion.
Yes, there's a suspension flow, that's what you're aiming at. Yeah. Now, it could be that alpha is equal to n. Then this 1 over thing doesn't make sense, so it definitely means infinity, which means that after you do the -1 over z flip, this geodesic is now pointing straight into the cusp. So if your alpha here becomes an integer at some point, then you then shoot into the cusp. When does it do that? Well, by the Gauss algorithm, by the continued fraction algorithm. The continued fraction algorithm stops precisely when your input is a rational number. So if your endpoint here is a rational number, then you do some winding up and down a few times, namely precisely how many digits your continued fraction expression has. And the digits tell you how often you wind until you come back. And then you shoot into the cusp and do not come back. So it's the geodesic flow and the continued fractions, they really go hand in hand. Very nice algorithm to understand. So there's one downside. I really could finish. So there's one downside to this picture, namely the quotient is not compact. So it doesn't quite fit into the discussion of the morning, but let's just agree to ignore that for now. It will haunt us, and there will be some features coming up later where this non-compactness really becomes important for us. But for now, let's just ignore it. We will calculate after the break the volume, see that it's finite, and then we have a dynamical system, at least in the sense of the second talk of the morning. Namely, we have a finite measure space which we can normalize to be a probability space, and we have some flow on that. Thank you, Mr. Coffey.